So assignment related to nuclear decay and binding energy. For this question, the penetration of matter by radiation depends on ionizing power of the radiation. Which of the statement is correct? We know alpha is having the highest ionization compared to that of beta, and beta is more than gamma. So alpha is weak ionizing, that is wrong. Alpha is having the highest ionizing, so the only travel few centimeter in air, that's two. Highest ionizing, lower range, like smaller range. Gamma is highly ionizing, that's totally wrong. Gamma is weak ionizing, so it is not very penetrating. No, it should, if ionization is weak, it will be very penetrating. So it can travel several kilometers in air. That's why option B is the right answer. So we have lead, which is radioactive isotope. It's emitting out radiation. So you can see the nucleon number does not change, but the proton number increases by one. It means it's a negative beta decay in which the neutron breaks down into proton and electron. So what should be X? It should be electron or a beta. If it was a positron emission, then the nucleon number remains the same, but the proton number decreases by one. In this one, which of the following statements is correct description of a binding energy of a nucleus? Look, it is energy released when the nucleus formed from individual nucleon. That's true. Because what happened, like when individual nucleons are there, they have more mass. When they form a nucleus, they will have less mass. So what happened to remaining energy? That energy will be released and that is used to hold these nucleons. So A is the right answer. Why not B? The energy released when the radiation is emitted from the nucleus. So why B is not correct? Because the energy radiated equals to increase in binding energy. Like if the energy radiate, basically if the question is what is the increase in binding energy, then statement 2 will be the right. As the energy released when the radiation is emitted from the nucleus. So in that case, the binding energy will increase as well. The energy required to overcome force between the nucleus. So energy which is required to overcome the force between the nucleus, that is also not correct. And the last one, what happened? The last statement, that energy required to remove nucleon from the nucleus. So the energy required to remove nucleon from the nucleus, that is the total energy, binding energy, but that is not binding energy. Like remove nucleon, that is like a binding energy per nucleon, that is not a binding energy. Because how much energy I need to remove one nucleon out from the nucleus is called binding energy per nucleon, but not the total. If it was a sum of binding energy of all the nucleon, then we'll say that is equals to binding energy. So binding energy is basically when individual particles, individual nucleon form the nucleus, then with their mass will decrease and that mass is converted into energy, and that energy which is released is known as binding energy. In question 4, half-life of protactinium is 70 seconds. After which of the time below would the activity of a sample decreases to less than 2% of its original value? So we will use a formula. First, we can work out because the half-life is given, so we can work out the decay constant. The decay constant is equals to 0.693 divided by T half. So this will be equals to 0.693 divided by T half, which is equals to 70. That will give us a decay constant and the answer will be in second inverse. I did not simplify, I'm writing in fraction. You can simplify and get in decimal as well. Now, we want, because the question is, after which time would the activity of a sample decreases to less than 2% of its initial value? So we have the formula A is equals to A naught e raised to the power minus lambda t. So if original activity is A naught, we want to find a time when the activity decreased to 2% of original value. 2% of original value means like 2% of A naught, or we can say 2 divided by 100 A naught, or we can say 0.02 A naught. So this will be equal to 0.02 A naught. And e raised to power minus the lambda we already worked out 0.693 over 70, and then t will be there. Then A naught will cancel with A naught because this A naught is common, so A naught will cancel with A naught. Then we simplify it because we want to remove this e, so we'll take ln both sides. So this will be ln 0.02 is equals to, when we take ln and e cancel out, this will be minus 0.693 divided by 70 into t. This will be negative answer, so minus will cancel with minus, or it will be 70 divided other side multiplied by ln 0.02 divided by 0.693. So this will give us time it will take for activity to decrease to 2% of its original value. So when we simplify, it will give us about 420 seconds. A technician is planning to use a radioactive source to check the calibration of a radiation counter. The source should have a large decay constant. The decay constant and half-life are inversely proportional. So half-life is 0.693 divided by lambda. So if it's having a large decay constant, it means the half-life will be short. So either A can be an answer or C. Then what about how many number of the unstable nuclei in the source should be large? Otherwise, if a technician use a very small number of radioactive nuclei, so it will decay because it's having a short half-life, so it will decay quickly. So the calibration, like the technician is not able to calibrate properly, as the radiation will change drastically because it's a short half-life. That's why the number of the radioactive unstable nuclei in the source should be large as well. So C will be the right answer. So a sample of a radioactive material is having a known half-life. Look, using a known half-life, you can determine its decay constant, and using a decay constant, you can determine the activity. The radioactive decay is random. This means we can predict. What we can predict, we can only predict its activity, like how many nuclei will decay every second. That is the thing which we can predict. So which one is representing that when a given nucleus will decay, we cannot predict. It's a random process. The time for whole sample to decay also cannot be predicted. Next nucleus will decay cannot be predicted. What we can predict, fraction of a sample that will decay in 1 second, or this is representing the activity. So we can only predict the activity of a sample, like how many nucleus will decay in 1 second. But what we cannot predict is when is the, like when a given nucleus will decay, specific nucleus will decay, or when the what will be the next nucleus will decay, or how much time the whole sample will take to decay. But what we can predict is the number of the atoms decay every second. If we know the half-life, we can determine the decay constant, and the decay constant we can determine its activity. So option D is the valid answer. So a radioactive sample is a beta emitter. Beta are able to pass through air only, not only air. Beta can pass through even paper as well. So thick card or a paper, it can also pass through. A thin aluminum will block beta. This will also block this, because here it's written air only. If it was the option air and paper, then it will be true. But air only, that's wrong. So that's why B is the right answer, that beta are able to pass through. A thick card. So why the alpha radiations are highly dangerous when they're taken into the body? Because alpha radiations are having the highest ionizing or very ionizing. That's why it is dangerous. So uranium-238 is emitting out alpha particle and we cannot influence. So if we cannot influence, if a reaction or a process can happen by itself or not affected or triggered by external factor, so that we call spontaneous. So radioactivity is spontaneous and random. If the question was, if we cannot predict which will be the next radiation, then we'll select random. But as I mentioned that it is a spontaneous, as I mentioned, it is impossible to influence. That means it is spontaneous.